Hello everyone, welcome to this lecture of linear control theory with lab, where we are going to talk about the step response of the systems. In the first part we'll see some basic concepts and then we'll go into more details. So first of all, we need to know why we are interested in the step response of the system. If you want to define the step response of the system, it's indeed what we get as the output of the system when we apply a unit step change at the input side of the same system. And it could be considered in two ways. In the first case, we assume that we have the system in the form of a transfer function here, g of s, which receives the unit step at its input. So u of s is equal to 1 over s, where 1 over s is indeed the transfer function that we have for the step signal. Okay, so for the step signal, we have the time domain representation like this. It's 0 before t equal to 0, and then it switches to 1 and remains as 1 at t equal to 0. Here we have t and u of t. So that's what we have for the step of t. U of t is equal to, I can write it here as well, 0 for t smaller than 0 and 1 for t bigger than 0. You can assume that it also includes the t equal to 0. Then in the Laplace domain, u of s is equal to 1 over s. So we apply u of s equal to 1 over s at the input side of g of s, and then we get y of s, and you know that it will be in the form of g of s times 1 over s. So this is what happens when we apply the signal at the input of a system. And as an example, we can assume that we want to see the change, the torque which is given to an electric motor. Okay, so we change the torque, and then we see how the velocity varies. The second case is when we assume that we apply the unit step as the reference signal to a closed loop system. So the closed loop system itself could be considered as a transfer function, t of s. It receives the reference signal and it will give us the output signal, which is again t of s is equal to c of s is equal to t of s times 1 over s. So basically we want to change the reference input of the closed loop system. We give it a sudden change, and then we want to see what happens to the output of the system. As an example, we can assume that we change the reference velocity to an electric motor, where we have a PID controller working in the closed loop form, and then we see how the velocity of the electric motor changes. Okay, so basically this will give us an idea of how the system behaves, and then we will have some, let's say, idea in which we can design the controller. Okay, so we will be able to design the controller referring to the step response of the system. We will analyze the behavior of the system, let's say, based on this step response. We can compute the step response in the time domain analytically if we know the transfer function of the system, whether in the closed loop or open loop format. And since we know the Laplace transform for the input signal, which is 1 of s, we can compute the output analytically by finding the Laplace transform of the output signal and then finding the inverse Laplace transform. Here we have two examples. I can show you how we do it indeed. So g1 of s is given in the form of s plus 2 over s plus 5. And if we have u of s equal to 1 over s, then c of s will be equal to s plus 2 over s plus 5 times 1 over s. We can find the inverse Laplace transform for the same system that we have here. If you have 1 at the numerator, we want to have s plus 2, so okay, so let me say it in this way, just to be quick. We will have a and b, and therefore for the c of t, you can find the expression a plus b e2 minus 5t, the whole thing times u of t. So you can indeed find the step response of the system in the time domain in this way by finding the inverse Laplace transform of the output signal. And you can do it for this case as well. In the case of G2, the response will include some sinusoidal signals as well. I guess it's something that you can do it on your own. So that's what we can do. But in general, we are interested in analyzing the systems by, let's say, saying the fact that what happens to the step response of the system if a parameter of the system changes. Let's say, for example, if the location of the pole of a system changes. If we have a first order system, I'm going to define the first order systems later. Let's say we have a pole here. What happens to the step response of the same system if that pole moves towards minus infinity, and instead of minus 1, it ends up at minus 5? How the step response of the system changes. So this is something that we are interested in, because this will help us in designing the controllers later. So to have this capability, we will go through the first order and second order systems to see how their step response is formed and how the step response changes while some parameters of the system changes. And first we start with the first order systems. Later we will have a look at the second order systems. A first order system is a system which has a single pole. You can see it here. So a over s plus a is a given system. It is called a first order system because it has a single pole at minus a. In this case, we have no zeros, but a first order system can have a single zero, let's say. And you can see that the DC gain of the system is also equal to 1. But this is a general consideration, okay? It could be different than 1. If we have this case, then C of S could be defined as A over S times S plus A, and then we can decompose it into 1 over S minus 1 over S plus A, and finally we will have C of t equal to 1 minus e to the power of minus A times t. And now you can see the effect of this A, which is the location of the pole of the system, over here. The exponent term for the step response of the system. 1 minus e to the power of minus A times t. So you can see that if A gets very small or if it gets very big, then the step response of the system will be changing. Since the location of the pole of the first order system is important, we define a term which is called time constant t, and it's defined as 1 over a, where a is the location of the pole of the system. Then we can rewrite the first order system in this form. Instead of a over s plus a, we will have 1 over 1 plus s times t, and the step response will be in the form of 1 minus e2 minus t over capital T. So the capital T is the time constant for the first order system. And we have seen that the step response depends only on t. And we have assumed that the DC gain of the system is equal to 1. For instance, we can find the value for the response of the system at time t equal to the time constant. So t is equal to t here, and it is equal to 0.63. And since over here the DC gain of the system is 1, meaning that the final value will be equal to 1, this 60.63 means that the response of the system reaches 63% of the final value at time equal to time constant, t equal to capital T. And you can see the graphical form of the step response here. At time equal to t1 time constant, we have 0.632, and you can see the values for the multiples of the time constants here as well: 95%, 98.2%, and 99.3%. Please also notice that C dot at 0 plus is equal to A. So, and we know that A is equal to 1 over T, because T was defined as 1 over A, and therefore the slope right at the beginning at 0 plus, which is here, the slope is equal to A. Okay, so that's something that is that gives us also a sense of how the step response will change if the location of the pole of the system changes. If pole moves towards the origin, if you have a pole here, okay, so let's say that we have a pole here at minus A. If it moves towards the origin, if A becomes smaller, then the slope that we have here also becomes smaller. So the, let's say, the step response of the system becomes, it takes a system longer time to reach its final value. On the other hand, if A becomes bigger, if A moves in this direction, then the slope becomes bigger as well, and as a result, the step response reaches its final value earlier. We will discuss about this rise time and settling time later in the next slides. You can also prove this result that we got here using the initial value theorem. Okay, so you should know how the initial value theorem works, and if you apply that, you will get the same, exact the same result that we have here. For the first order system's step response, we define some parameters. There are some important parameters that we define and use. The first one is the rise time, and the second one is the settling time. Regarding the rise time of the first order systems, or T underscore R, it is the time for C of T for the output to go from 10% of the final value to the 90% of the final or steady state value. For the first order system, it could be approximated as 2.2 times the time constant. On the other hand, the settling time, or T underscore S, is the time for C of T to reach and stay within a given percentage of the final value. Usually we define it for the 5% and 2% settling time, and in each case you can see that it's a multiple of the time constant. For 5% settling time, it is 3 times T, and for 2% settling time, it's equal to 4 times T. One important fact here is that you can see that both of these parameters, the rise time and the settling time, they depend on T only. So the time constant, which is basically related to the location of the pole of the system, determines the behavior of the step response of the system. This is something which is quite important. You see how important is the location of the pole of the system. You can also see in this graph how the settling time and rise time are defined. The rise time is the time which it takes for the system to reach from 10% of the final value to 90% of the final value. So this time in it. And the settling time is when the response of the system reaches and stays within a given percentage. So in this case, 2% settling time is considered, and this is the settling time. Here in this example, we have a system g of s equal to 100 over s plus 50. We need to find t. I guess it's quite straightforward. So a is equal to 50, therefore t, the time constant, will be equal to 1 over 50 or 0.02. And then we want to find out the TR rise time. It's 2.2 times t, or 2.2 times 0.02. And the settling time 2%, which is equal to 4 times t, 4 times 0.02. You can just do the multiplication. So this way we know how the step response of a first order system is obtained, and how the important parameters that we have depend on the location of the pole of the system, which determines the time constant of the system as well. So here we have minus a, and t is equal to 1 over a. Rise time is equal to 2.2 times t, and we have the expressions for the settling times. Okay, in the next lecture, we will discuss about the second order systems, and we will see how different they are from the first order systems. Thank you for watching.